Okay, basic principles of polymers. Okay, so in this class, first we'll learn about what polymers are. Okay, so what is exactly polymer? So poly in English means many, right? And more means part or unit. Okay, so basically polymer means many parts, so it consists of many parts. Okay, since it consists of many parts, its main characteristics include high molecular weight. So polymers generally have high molecular weight, and high molecular weight afford many interesting physical or chemical characteristics. Okay? And polymers are based on organic materials. So if you recall from organic chemistry class, organic means that the compounds are based on carbon-based materials. Okay? So basically, carbon-based materials shows very high molecular weight. To do that, those carbon-based materials should be connected by chemical bond. Right? Okay. Then we need to know what kind of chemical bonds are present in polymeric structure. Okay. If you recall from general chemistry class, there are two different kinds of bond. Okay. The first kind of bond are primary chemical bond, and secondary chemical bond. And there are three different kinds of primary bond, which are covalent bond, okay, ionic bond, and metallic bond. Okay. And since polymers are basically organic materials, right? If you recall from organic chemistry class, all organic materials, not all, but almost all organic materials consist of covalent bond, right? So polymers are basically formed by covalent bond between different types of carbon-based materials. Okay. Also, there are secondary interactions, so which include hydrogen bond. Okay. For example, dipole-dipole interaction, and van der Waals interaction. Okay. So there are also secondary interactions inside of polymer structures. Okay. So we said that polymer means many parts or many units. So what is exactly parts or unit? So there is a certain unit inside of polymer structures. So for example, let's draw a polymer structure which is polyethylene terephthalate, PET. Okay, familiar with us. So PET have this kind of chemical structure. Okay. So inside of this parenthesis, okay, there is a basic unit with these structures, and here is N here, which means that these basic structures repeat itself by N times, right? Okay, so these basic structures, which is the basic form of this polymer PT, polyethylene terephthalate, is called repeating unit. Okay, so all polymers have this basic unit, which is called repeating unit. Okay, that repeating unit repeat itself many times, by n times. As a result, they show very high molecular weight. Okay? All right. And we have already have learned that polymers have high molecular weight, right? Then, why do we need high molecular weight? What if we only have very small molecular weight of polymers? Okay. We'll learn about that later in later sections, that this molecular weight determines many physical or chemical characteristics of polymers. Okay? Especially high molecular weight polymers have very good characteristics which can be used for various types of applications. Okay? So we need to know basically how to control this molecular weight, what determines the molecular weight, and also how different molecular weights affect different physical or chemical properties. Okay? So we learn about one by one in later sections. Okay? All right. So polymers are basically high molecular weight from a certain repeating unit. Okay? And also they should be connected with a certain order. Something like this, right? With repeating unit, they repeat itself many times. Okay? Okay? Well, there are some molecules which also have high molecular weight, but they don't really have repeating unit. For example, let's recall the structure of DNA or RNA. Okay? Their repeating unit is the base, right? Adenine, guanine, thymine, something like that. But there is no specific repeating order, right? Consisting of this DNA or RNA structure. Okay? There's no specific order. Okay? So although DNA or RNA have very large molecular weight, we cannot really say that these are polymers. Okay? Instead, people say these kind of molecules with large molecular weight itself called macromolecule, which means they're very big molecules, right? Okay. So polymers are also macromolecules, but they not only have high molecular weight, but they also have specific repeating unit, repeating order, right? That's the difference between polymers and DNA or RNA, right? So, in other words, polymers are relatively smaller concept compared to macromolecules. Okay? All right. Then how do we represent polymers? Okay? As we have already seen in the structure of PT, polymers are basically the connection of repeating unit with high molecular weight. So this A is repeating unit. Okay? But it's not really convenient to write the molecular structure of polymers like this. So we denote it as A sub N. Okay? All right? And how can we call the structure of specific polymers? How do we name the polymers? So we basically say these kind of polymers as poly something. Okay? Inside of here, they could have the name could be from the chemical structure of repeating unit or the substance of the repeating unit or just the product name. Okay, for example, PET, polyethylene terephthalate. Remember, for PET. PET is the abbreviation of polyethylene terephthalate. Okay, and if you recall from the previous structure, this. So here is ethylene structure, ethylene glycol actually. This is terephthalate. So basically PET, the name itself has the chemical structure. Okay. For substance, for example, PS or polystyrene, which basically look like this. Okay, and this polystyrene is made from this. This is the basing unit, or the we call it monomer. We'll get back to that point later. Okay, so this is the basic substance which are used to make this polystyrene. Okay, so we call this structure as polystyrene, the substance, or sometimes we call just simply product name. For example, like nylon. Nylon is a very common substance product name. So we'll learn about the nylon later. Okay. All right. So let's see some examples of polymers. So we have already seen polystyrene. Okay, so this polystyrene basically means that these structures are connected many times. Okay. Something like this, right? Okay. There are also similar polymers with similar structures, which is called vinyl polymer. So there are some examples of polymer. So we call this kind of polymer structure as vinyl polymer. And depending on the structure of this X substituent, you could have different polymers. If X is simply hydrogen, then that is just polyethylene, or just we say PE. If X is methyl, the resulting polymer is polypropylene, or PP. If X is benzene group, then we have polystyrene, right? If X is chlorine, the resulting polymer is polyvinyl chloride, or we say PVC. Okay? Okay? Right. Okay. So we have seen a few examples of polymers. Okay. Now let's move on to the structure of polymers. Okay. So if you look at these vinyl polymers, since each element is connected by covalent bond, okay, they could have different structures, such as, so let's say these vinyl polymers, something like this. HX. So for example, this X, the substituents can be located in the same position, okay? Or it could be located in this way. So one position up, down, up, something like this, okay? Or the position of X could be just random, okay? And all of these structures, or random position of these substituents X, okay, cannot be interchangeable without breaking the chemical bond, right? So these kind of structures, these kind of different chemical structures, polymers, are called configuration. So polymers have different configuration, okay? So different configuration gives different tacticity of polymer, okay? So the first structure, this structure, is called isotactic structure, and this structure is called syndiotactic structure, and this one, random position, or tactic structure, okay? So either isotactic or syndiotactic polymers have very ordered structures, right? Compared to random, these two, compared to this one, are relatively very ordered arrangement of X, the substituents, okay? So these isotactic or syndiotactic structures afford crystalline structures. So we'll get back to that later. And this random position of X gives us amorphous polymer. Okay, so we'll get back to this point later. Okay. All right. So another example of configuration. So this is the configuration. Okay. So another example include cis-trans configuration. Remember from organic chemistry class, right? So for example, let's see polydiene. Okay. So polydiene, the basic unit, have this structure. Okay. If you make polymer with this unit, so there are 4 different carbon, 1, 2, 3, 4. If you do 1, 4 addition, which result in this kind of structure. Okay. So here is double bond, carbon-carbon double bond. Okay, so which could have 2 different structures, right? Something like this. Sorry. So I'm going to try it again. The resulting polymers would have either these structures or this structure, right? Either cis or trans, which cannot be interchangeable, right, without breaking the bond, right? Okay, this is another example of polymeric configuration structure. Okay, there's also concept of polymeric structure, which is conformation. Okay. So conformation is basically because polymers are connected by covalent bond. Okay. So let's say that we have, for example, like have normal butane, which have these structures. Okay, but in reality, this normal butane does not have these linear structures, right? They have three-dimensional structures, something like this, right? C, 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 C. All bond can be rotated, right? Okay, so if you look at the position of each carbon from this side, for example, from here, we have I here. Okay, we could have different structures, right? Since they can rotate something like this, right? And the resulting projection is called Newman projection, right? You already have learned it from organic chemistry class, right? Okay. So depending on the overlap of different carbons, they could have different overall potential energy, right? Yeah. So the details will be covered later. Okay. So overall, polymeric structures have configuration which cannot be interchangeable without breaking the chemical bond, and also conformation. Okay. Today we'll also learn about the different kinds of polymers, different like categories of polymers depending on the sequence, structure, molecular weight, etc. So if you recall from previous class, polymers basically means many units, right? So if you have repeating unit, or we call it as monomer, such as A, we can synthesize polymers from this repeating unit, and we can represent it as a N. Okay, so this is repeating unit. Okay, and depending on the type of like three-dimensional structures, they could have different structure, different configuration, which cannot be interchangeable without breaking the bond, chemical bond, and also conformation, right? All right. So let's categorize polymers depending on different types of characteristics. First, sequence. Okay, so depending on the sequence, polymers can be divided into homopolymer and heteropolymer. Usually we call heteropolymer as copolymer. Okay, so homopolymer is basically the polymer with single repeating unit. So basically has same repeating unit of A. Okay. On the other hand, heteropolymer have different types of unit. So they could have different structures such as block copolymer, alternative copolymer, or graft copolymer, or random copolymer. Okay, so first, block copolymer has structures with A block connected with B block, something like this. So there is one type of monomer, different type monomer, could be another type, etc. Okay. So we usually denote block copolymer as poly A block B, something like that. Alternative copolymer, as the name indicates, the repeating units are arranged in alternative fashion, A, B, something like that. Graft copolymer is, we have linear polymer, and there is some like branch of another polymer unit, something like this. Okay, and random copolymer is just random arrangement of different repeating units. Okay, this is the categories of polymers based on the sequence. Next, based on structure. Okay, so first kind, linear polymer. So basically it has linear structures, linear like arrangement of the polymer chains. Branch polymer, as the name indicates, there's some branches. So depending on the length of the branches, it could be short branch or long branch. Third type of polymer is called network polymer. So it has basically network structures like this, right? And the importance about this polymer structure is that depending on the polymer structures, it can be processed in different ways. Okay? The reason why is that if you look at this linear or relatively short branched polymers, which means that the molecules, the chains, polymer chains can move relatively freely. Okay, so it can be basically molded. Okay, when you make some kind of products using polymers. Okay, so these kind of moldable polymers are called thermoplastic. Okay. On the other hand, since network polymer, all the polymer chains are connected by this chemical bond, they cannot be molded. Okay, so mold is impossible. Okay, so once they form these kind of network structures, they cannot be remolded. So these kind of polymers are called thermosets. Okay. So depending on although the chemical structures are basically same, but overall the macromolecular structures are different, and depending on those kind of structures, they can be processed in different ways, and they can have totally different physical characteristics. Okay, right? So, if you look at the textbook, there's this figure. The polymers can be divided into different kinds, actually 3 different kinds. There is thermoplastic, as I mentioned, which can be molded, okay, based on the melt. When you increase the temperature of the polymer solutions, polymer samples, it basically liquefies, okay, and that liquefied state of polymers are called melt or viscous liquid. Okay, the one kind is thermoplastic, the other kind is thermoset. Okay, next kind is elastomer, such as like rubber band. Okay, and also thermoplastic can be categorized into crystalline polymer and amorphous polymer. Okay, and we'll get back to this point later in more details. Okay. So the important thing about this is that depending on the structures, they have totally different properties, and that determines the basically what kind of applications we can have with specific type of polymers, and especially at what temperature can we use, can you mold it or can you use it, something like that. Okay, so next category is size of the polymer. So since polymers are very large molecule, size means basically molecular weight. So depending on molecular weight, polymers could have different structures and also different properties. Okay, so for example, let's consider polyethylene. So polyethylene is basically made from ethylene, okay, which is actually gas. Okay. And by doing the synthesis or the polymerization process, we can form the solid polyethylene material. Okay. And this polyethylene, depending on the density, which have very different types of polyethylene, HDP, LDP, LLDP. Okay, we already have seen that the molecular structures of polymers determines the physical properties. So HDP means high density polyethylene. So density is very large. Okay, so if you go back to these structural properties, if the molecular structures of polymers are, for example, linear or short branched, okay, you can imagine that the packing molecular polymer chain, the packing of polymer chains would be more efficient than, for example, like long branched ones, right? If the packings are more efficient, which means that there could be more molecules, more polymer chains given for a given volume, which could result in higher density, right? So usually linear polymers afford high density properties, okay? So high density polyethylene is usually used for like some kind of plastic bag basket or something like that with relatively large strength, okay? Also, low density polyethylene, okay, if the molecular structures are relatively like long branch or like something like that, the overall polymer chains cannot be packed efficiently compared to high density case, right? Okay, so low density polyethylene is usually used for like some kind of thin film that we use when you make the food in the kitchen, right? And another type of polyethylene is LLDP, which is linear low density polyethylene. So linear polyethylene results in high density polyethylene, but if it has some branch, even linear polyethylene can have relatively low density, okay, which have different physical properties. Okay. Right. So since the size or density is important, so we also need to learn about the molecular weight of polymers. Okay, what kind of molecular weights are? There are many different types of molecular weight for polymers. Usually we denote 4 different kinds. The first one is number average molecular weight, denoted as MN bar. Second kind is weight average molecular weight, denoted as MW bar. Z average molecular weight, MZ, and viscosity average molecular weight m3 bar. Okay. So there are more different kinds of molecular weight for polymers, but people usually denote these 4 different kinds, and usually these 2 are used to characterize the polymer sample, specific polymers. Okay. All right. And we'll learn about that again later, but anyhow, let's define another variable which is called polydispersity index, denoted as PDI, which is defined as the ratio between weight average molecular weight and number average molecular weight. Okay. All right. So let's see what exactly these different kinds of molecular weights are and how they are defined. Okay. And before moving on, why exactly the molecular weight important? Okay. So why do we really care about molecular weight? If you check any physical properties of polymers as a function of molecular weight, generally has this kind of dependence. Okay? When molecular weight is relatively small, the physical property is not enough, but when molecular weight is above a certain level, the physical properties have relatively constant value. Okay, that's why molecular weight is important, and we need to define the molecular weight of specific polymers. Okay, all right. So let's define each of these molecular weight. The first one, number average molecular weight, is defined as just simple average. Mi over Ni. Okay. So here, Mi is the molecular weight of different length of polymers, because all polymers have the various types of molecular weight. Okay. So, and N is the number of those chains with specific length. Okay, this is simple. Basically, total weight over the total number of chains. Okay, so since we can denote this part, this part, okay, Ni over the sum of the Ni as mole fraction, not mole fraction, number fraction. So this number average molecular weight can be written as fraction times molecular weight of each chains. Okay. Secondly, weight average molecular weight is defined as Ni square. This is the definition. Okay. And the sum of the overall chains are basically the weight, okay, of each chain. So it can be expressed Wi over I Wi Mi. Okay. Or if you denote small w as the weight fraction, so this is the weight fraction, then we can write it in this way. Okay, so this part is basically small wi. Similarly, Z average molecular weight is defined as Ni Mi square NiMi to the third. Okay, and viscosity average molecular weight is defined in a little bit different way. NiMi over NiMi 1 plus I 1 over A. Okay, here A is some number between 0.5 to 0.8. Okay. Right. So, if there are no molecular weight distribution, if all the polymer chains have exactly same length, okay, which we call that situation as monodisperse. In that case, all the molecular weight would have the same value, right? Since there are only one specific length of the molecular weight, okay? But in general, it's not the case, okay? So the other case, if there are molecular weight distribution, we call it polydisperse. In general, if you check the relative scale of these different kinds of molecular weight, generally Mn is the smallest one. V, M, W, M, Z. Oh, sorry, Z. Okay, so if you have like molecular weight and some proportion, usually have distribution something like this, right? So usually this part is like Mn, Mv, W, Mz, something like that. Okay. All right. So we have introduced different kinds of molecular weight. Okay. All right. This lecture we'll cover the contents about molecular weight determination. Okay. So in previous class we have learned about the different kinds of molecular weight of polymers, right? There were number average molecular weight, weight average molecular weight, viscosity average molecular weight, Z average molecular weight. And we learned about the definition of each of these molecular weight, okay, and some related calculations. Okay. Okay. So today we'll learn about how experimentally to determine these different kinds of molecular weights. One thing to note is that in most cases of experimental determination of molecular weight, we are basically assuming dilute solution of polymers, basically. Okay, the dilute solution behavior is very important in determining the molecular weight of the polymers. Okay, because if there are too high concentration, too much polymers, the overlap of polymers occur, so it's not really easy to determine the molecular weight. Okay. Overall, there are two different types. The first type is absolute molecular weight determination. Second type is relative molecular weight determination. Okay. Among absolute molecular weight determination, there are end group analysis, especially in step growth polymerization, titration, NMR, boiling point elevation. Similarly, freezing point lowering, or vapor pressure lowering. Using this method, titration, NMR, boiling point, and vapor, etc., we can determine number average molecular weight. Okay. Other methods include osmotic pressure measurement. We learned about it in physical chemistry class, right? This can also determine number average molecular weight, and light scattering. From this, we can determine weight average molecular weight. The light scattering and centrifugation. Centrifugation is actually about Z average, but anyhow, okay, let's remember this. Okay, this is the various types of absolute molecular weight determination method. For relative method, the first kind is gel permeation chromatography. Okay. Or in other words, we say size exclusion chromatography. Another method is viscometry. By measuring the viscosity of polymer solution, we can also determine the molecular weight. Okay. By measuring the measuring the viscosity, we can determine the viscosity average molecular weight, MV. Okay. All right. So let's see some of the details about this relative molecular weight determination method. The first is viscosity measurement, viscometry. Okay. So basically, viscosity measurement of dilute polymer solution. Okay. To do that, we are basically using this kind of tool. Okay. So inside of this, there is a tube here, and there is capillary. So here's a very thin capillary. Okay. So we pour basically the solution, or polymer solution, at time is 0. Okay, and it flows through this, and we measure some time here, time experiment. Okay, we basically can experimentally measure the time difference between at the beginning of the pouring and when the solution touches this point. Okay, this narrow capillary, this capillary basically provides resistance to flow. Okay. So measuring the time is very easy, right? You can first measure the time of the polymer solution. So time of the polymer solution, and time for solvent. And you can compare them. Okay. Then by comparison that number, you can determine the viscosity, because the flow time of the solution is proportional to the viscosity. If the solution is viscous, it takes more time, right? So time of the polymer over time for solvent should be, so it can be like T0, something like that, should be proportional to the viscosity of the solution to viscosity of the solvent. Okay, it's very simple, right? Okay. Okay. So you determine the viscosity of the solvent and viscosity of the solution, polymer solution. Okay. And by simply measuring the time of the flow of the solution, you can determine it. And the ratio of the viscosity of the solution and solvent is called relative viscosity at R. Okay, and this is relative viscosity, and this relative viscosity is a function of concentration. So it has this kind of form: some constant concentration, some other constant, something like this. You can express it as infinite series, right? And there is another term which is called specific viscosity. Specific viscosity as P is defined as the relative viscosity minus 1. Okay, so which can be expressed in this way, right? Another term which is called either reduced viscosity, viscosity, reduced to specific viscosity, which is defined as the specific viscosity over concentration. Okay, so which can be written as A0, A1C, A2C square, square, like this. Okay, and there are a lot of terms, right? Specific viscosity, reduced viscosity, intrinsic viscosity of any solution, which is defined as the reduced viscosity as concentration approaches 0. So which is equal to, from here, A0. Okay? Right? Okay. So this is intrinsic viscosity. Okay? So what you need to do experimentally is very simple. Okay? You experimentally plot x-axis is concentration and y-axis to be this number, okay, which is actually over C this, okay, which can be experimentally measured by T minus T0 over C T0, right? You plot it as a y-axis, okay? Then what you will get is this kind of data. Okay? And if your approach is basically, if you take the limit of C approaches 0, this y-intersect, which should be A0, intrinsic viscosity. Okay? So we can determine viscosity. Okay? Alright? And this viscosity, which is usually denoted as at the bracket, okay? Okay? This experiment determined the intrinsic viscosity has relation following this equation. Some constant times viscosity average molecular weight to A. And this equation is called Mark-Hovink equation. And this constant K and A depend on different combination of polymer and solvent, and also depends on the temperature. And usually this constant A for normal neutral polymer, electrically neutral polymer with a flexible backbone, A is in between 0.5 to 0.8. Okay. Right? Okay. So this is about the viscometry, how to determine molecular weight using viscosity measurement. Next method is based on gel permeation chromatography. From this measurement, we can determine the whole molecular weight distribution of polymer sample. Okay? So, we all know what chromatography is. So inside of column, there is some support which consists of porous gel or porous support. There are some size of pores. Okay? So there are many small pores inside of this support. And we elute polymer solutions, polymers like this. Okay? If polymers are really high molecular weight, meaning that it's very long chain, like this, compared to short chain, this long chain, this short chain polymer, short polymer chains will go inside of these pores, in and out of these pores, okay? While these long chain polymers basically cannot go into these small pores, they just elute through the support. So these high molecular weight, long chain polymers elute first, followed by relatively short chain, small molecular weight polymers. Okay? So if you plot the intensity as a function of elution time, you'll have this kind of distribution, right? So the long so this is time 0. Okay, so at the beginning we'll have high molecular weight polymers. At later time we'll have low molecular weight polymers. Okay? So basically by checking the intensity, we can determine the concentration of the polymers with specific polymer chains or molecular weight. Okay? Okay? And I already mentioned that this gel permeation chromatography, or GPC, basically is the method which can determine relative molecular weight. The meaning is that we first need to have calibration curve. Calibration curve with non-molecular weight, basically the monodisperse standards, and we learn the real solution sample, and by comparing the elution time, we can determine the molecular weight of the specific sample. Right? Okay? Because the molecular weight of the log molecular weight is relatively show linear response within a certain region. Okay? So using this linear calibration curve, we can determine the unknown sample, the molecular weight of unknown sample. Okay? All right. Okay. Next method is osmotic pressure. Actually, we only already have learned about it from physical chemistry class, right? Osmotic pressure pi is equal to concentration RT, right? Remember? Okay. Especially for low molecular weight solid. Okay. For polymers, we can use similar equation. The pi, or the molecular weight. So in this equation, this concentration is basically the the molecular weight of the since it's the molar concentration, which is basically the molecular weight of the solute over concentration RT. Right? Not really. Sorry. So anyhow, it's proportional to the molecular weight of the solute 1 over molecular weight. Okay. So for polymer, we can determine the molecular weight of the polymer by experimentally determining limit of osmotic pressure over concentration, which gives us RT over Mn. Okay, so if you plot pi over RTC, okay, as a function of concentration, what you will get is this kind of graph. Depending on the type of the solvent, it shows different behavior, but anyhow it is linear. So by putting this line, we can determine this y-intercept, which gives us the molecular weight of non-variable G molecular weight. Okay, so this graph is for good solvent, zeta solvent, or bad solvent. Anyhow, they gives us a linear line for the determination of the molecular weight. Okay, so in this lecture we'll cover the contents about polymer solubility. Okay, so let's say that we dissolve polymer in a certain solvent. Okay, as any molecules does when it is dissolved in a certain kind of solvent. Okay, some solvent would dissolve it, but some other solvent will not dissolve it. Okay, for solvent, we denote the solvent which can dissolve it as good solvent, and solvents which do not dissolve polymers well are denoted as poor solvent. Okay, and the question is, what exactly determines the good and poor solvent? And how does this polymer solubility in a certain solvent determined by thermodynamically? Okay, thermodynamic determination of polymer solubility. And is there any indicator which shows which solvent is a good solvent or which solvent is bad solvent? Not bad, poor solvent. Okay. All right. So there are several factors which should be considered in dealing with polymer solubility in a certain solutions. So, first question: what solvent what solvent will dissolve which kind of polymers. Okay? And that solubility, how does that polymer solubility is influenced by polymer solvent interaction. Okay? There will be many factors, right? So there are general rules for polymer solubility. So general rules for polymer solubility. First rule, like, dissolve like. Okay, this is obvious for any kind of solubility, right? For example, polar solvent will dissolve polar polymer, right? Non-polar solvent will dissolve non-polar polymer, right? Like dissolve like. Okay? Any solvent which can form hydrogen bond will dissolve polymers with, for example, like hydroxyl group, something like that. Okay, that's the first rule. Second rule, as the molecular weight of the polymer increases, then solubility decreases. That's also obvious, right? If the molecular weight increase means that polymer chain length increases, right? Compared to this polymer, if the length is much longer, then dissolve it by a certain solvent will be much more difficult, right? Because dissolving means that the solvent molecules surround the polymer chains around them, okay, completely. Okay. That will be much more difficult in this case, okay? So, as the molecular weight increases, solubility generally decreases. Third rule, crystallinity. As the crystallinity of polymer increases, solubility also decreases. Okay? That's also similar. You can understand it, right? Similarly in this way. Okay? If the crystallinity is larger, which means that the molecules are stronger, or the molecular polymer chain packing is much more ordered, right? Then it will be much more difficult to dissolve it. Like this disrupt those polymer chain packing. Okay. Fourth rule: as the cross-linking density increases, solubility decreases. Okay. If there are many cross-linkings inside of polymer chains, instead of dissolving it, just swells. Okay. How about not cross-linking? How about branch? In terms of branch, if there are relatively short branch, it usually helps, like to rate of solubility usually increases, because short branches help for solvent to penetrate into the polymer chains. On the other hand, if there are long branches, long side chains, because of the entanglement between these long polymer chains, it makes the individual polymer chains to separate with each other, so solubility decreases. Okay, these are the general rules about the polymer solubility. Okay. Okay. And let's try to consider polymer solubility in terms of thermodynamics. Since we all have learned about thermodynamics in second year, which solvent at which condition would the polymers will dissolve? It's very simple, right? Thermodynamics tells us that delta G is equal to delta H minus T delta S. That's pretty much it. If the Gibbs free energy change for dissolving the polymer in a certain kind of solvent is negative, then that process is spontaneous. Right? Okay? If it is positive, they will not mix. The solvent will not dissolve. It's immiscible. Okay? That's pretty much it in terms of thermodynamics. Okay? Okay? So there are several models which try to describe the polymer solubility or the dissolution of polymers inside of solvent. One model is called lattice solubility model. So in lattice solubility model, we have this kind of lattice. Okay, and there is, for example, this circle is a certain molecule, and it is surrounded by solvent molecule. This blue circle is solvent. So the blue one is solute, and the blue one is solvent. So by putting solute and solvent molecules in a certain kind of lattice, okay, this model tries to calculate if they can mix together or not. For polymers, we also need to consider polymers are basically connected with each other, right? Long chain, right? And is a solvent. Okay, so for polymers, if this is the case of low molecular weight solute, then for polymers, the model should be modified. It will be much more complicated, right? So statistically, we can model a solution of polymer in this way, but it's more or less complicated, right? Complicated approach. So people found much more easier, much more convenient way to determine which solvent will dissolve which polymers, which is called solubility parameter. So solubility parameter, as defined by Hildebrand, is given in this equation: delta solvent mixture is given by x1 nu1 delta 1 x2 nu2 delta 2 over x1 nu1 plus x2 nu2. Okay, here x is the mole fraction inside of the mixture, and nu is this is mole fraction, and nu, actually v, is the volume, molar volume. Okay. and this delta are solubility parameter of each component. Okay, if you mix two different components, for example, two different solvents, okay, each solvent has a certain parameter, delta value, okay, and you can calculate the solubility parameter. Okay, and based on the solubility parameter of each component, you can calculate delta H, which is given by phi 1, phi 2, delta 1 minus delta 2 square. Okay. So if delta and delta 2 solubility parameter of each component, the difference of each solubility parameter is small. If delta 1, so basically if this is small, which means that delta H is small, okay, then in delta G is equal to delta H minus T delta S. Since delta H is small, it's much more probable that we would have negative delta G. Okay? But if delta H is large, large means positively large, okay? Because all these values are positive, right? This is positive, and these two values are just volume fraction of each component, so it is positive. Okay, so if delta H is positive and large, then delta G would much more probably be larger than 0, so it will not mix. Okay, so as a rule of thumb, when the solubility parameter of two components, for example polymer and solvent, are smaller than 0.5, usually they dissolve. Okay, if it's larger than 0.5, they are immiscible. Okay? And this solubility parameter delta can easily be determined. So solubility parameter delta can be determined experimentally by swelling experiment. So you prepare for dry polymer, okay, and you mix it with solvent, and you just measure the degree of swelling. Okay, if it swells like infinitely, which means that it dissolves it completely, right? But if it's not, it swells a certain amount, right? Like the change of the volume or height, right? Usually by measuring the change of the mass by swelling, by observing the solvent molecules, we can determine the degree of swelling and as a result the solubility parameter. Okay. So for example, if you plot the degree of swelling as a function of like the solubility parameter with different kinds of solvent, like different kinds of solvent, and you prepare for dry polymer, okay, and you add, like for example 10 different kinds of solvent with different solubility parameter, okay, then you can determine the degree of swelling like this, okay? Like this, okay, and the maximum point of swelling is denoted as the solubility parameter of that polymer. Okay. Alright, so this solubility parameter is based on Hildebrand, and there is another solubility parameter which is called Hansen's three-dimensional solubility parameter. So it's, the Hansen's solubility parameter delta is given as delta p square delta d square delta h square over root. Okay. Here, each solubility parameter is represent polar contribution, disperse contribution, hydrogen bonding. So basically, Hansen's 3D solubility parameter considers the secondary molecular interactions. Okay. Dispersion for polar fold interaction, dispersive interaction, and hydrogen bonding. Okay. And the value of each of these components and the resulting solubility parameter is given for various types of solvent and polymer. For example, the Hansen's solubility parameter delta for, let's say, chloroform is 9.36, THF 9.5, methanol 14.5, toluene 8.91, water 23.5, and for polymer, this is for solvent. For polymer, PS, polystyrene, is 9.33, just monomer styrene, 9.32. So if you look at the number, the polystyrene has solubility parameter of 9.33, okay, and toluene is 8.91. Chloroform, THF, all close to each other, right? And the difference between the 9.33 and these solvent are less than 0.5, which means that chloroform, THF, or toluene will dissolve PS. Okay? But the parameter of methanol or water is much larger than PS, which means that methanol and water cannot dissolve polystyrene. Okay? So, as a result, good solvent and poor solvent. So for good solvent, basically delta, the solubility parameter between solvent and polymer closely match with each other. But for poor solvent, it is not. Okay? Okay, and especially from thermodynamic approach, when delta G is equal to 0, okay, which means that delta H is equal to T delta S, this condition is called theta condition. And there are some solvent which gives us this condition, delta G is equal to 0, and that solvent is called theta solvent. Okay, exactly the boundary between solvent, good solvent and poor solvent. Okay.